La 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 la. La 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 la. All right, we're continuing in our quest. I had to take a phone call. I made a mistake. I didn't come back right away. I got distracted. Distracted. Big mistake. Big mistake. Big mistake. I'm not gonna take another phone call. That's it. They'll wait until I call them when I decide. If and when I decide to call. We want to listen to these. All right, let's listen to our no new threats. That's good. Audio is terrible. Oh, it's not noticing the microphone. Unplug the microphone. Unplug the microphone and replug it.
La 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 la. That should be better. Well, it's live. Should be much better now. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. Okay, hopefully it's much better. We'll check it later. Let me make sure Discord audio is similar. USB, no. No. The output is the headphones. Okay. What about this guy? What is the output? La 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 la. Headphones. Yeah, that should be good. Yes, it's good. It is good. Let's check the audio settings. They look good. Everything looks good. All right, we're good. All right. So what do we want? We were in the middle of doing something. We were definitely doing something. We were reading and doing something. All right. So we were watching this guy. So I was thinking. So all he's saying is that um, the electric field of the sheet. I guess the sheet is the cross section. Is relative. Is correlated to the negative constant of the derivative. I don't know why. It's like he's assuming a sine, so he's getting a cosine. I don't know.
A constant times the derivative of the electric field of the light shining on it. So our light hitting the electrons is just a wave, which would be modeled by some constant times a cosine function. So that means that the electric field produced by the moving electrons is the derivative of the cosine function, which is a sine function.
So I guess what he's saying is that the input is related to, the output is correlated to the derivative of the input, which is a sine function, so it's a cosine function. Okay.
What this means is that the electron electric field is offset by 90 degrees from the incident.
What do you mean electron electric field? The electron input or output?
Electric field. So when the two electric fields combine, then the electric field gets shifted back a little bit. The red line here represents the incident light wave shining on the material. And then the blue wave represents the wave produced by the wiggling electrons. So the result is a final wave that's shifted back a little bit from the red line. And so the new light after that first layer of electrons is now this black line. And then that black line hits the next layer of electrons and gets shifted back again. So every layer of electrons that the light hits shifts the electric field back a bit. So the total effect of this would be that the total light wave appears to be moving slower when it's moving through the material. But really, all of the electromagnetic waves are moving at the speed of light. But the combined wave peaks are actually propagating slower than the speed of light. So does light ever slow down?
I don't understand. I have no idea. How can, I mean, it looks like the waves are slowing down, so I don't understand. Let me see the thing.
Wave peaks are actually propagating slower than the speed of light.
So, I mean, what is the speed of light if not the propagation itself? Isn't the propagation, isn't that the speed of light? I mean, the speed of light is not the speed of a particle, it's the speed of wavelets. But these wavelets, they're just waves. They're tiny waves. They're little waves. As each wave waves through you, it waves through you at a certain, there's a certain propagation. There's a certain speed of propagation. Usually through the vacuum, so the way I would explain it is the ether, it's vibrating through the ether. But if it's interacting with a medium, then that could have second-hand effects, which could whatever. Whatever. I mean, these are just explanations. The question is, has the speed of light, has it been slowed down? And we saw that you're getting longer results. The same apparatus gives you longer, like we were getting 30% longer length, which means that it's, I mean, what else could it mean besides, right? The way if it works the way you explained, then it shoots a beam, it shoots a signal and waits for it to come back. So if it takes longer, that means it has slowed down. If you're explaining it now, you're just coming with an explanation. The explanation is that it slowed down. So you're just giving us an explanation, and you're not coming up with a prediction. So what are you trying to ask?
But the combined wave peaks are actually propagating slower than the speed of light.
That's it. So what else is the speed of light if not the speed of propagation?
Speed of light. But the combined wave peaks are actually propagating slower than
propagating slower. That's the definition of the speed of a wave.
Speed of light. So does light ever slow down? Well, no and yes.
What do you mean no? I don't understand why you say no.
Fundamental propagations of the electromagnetic waves always move at the true speed of light.
Wait, what? What are you talking about?
But the end result that we can actually measure in a real transparent material is that the electromagnetic wave peaks are slower. Now,
so therefore, you're saying that the incoming light goes through at the speed of light? Then you should not get the result with the reader, with the phone. Your phone LiDAR, whatever, was getting the signal back delayed. So according to you, it was never delayed. I don't know. I mean, so you just need to tell me, was it delayed? Was it not delayed? You said it is delayed. It looked like it is delayed. The way you explained it, it was delayed. Your explanation now is yes and no. What do you mean yes and no? It's yes, it got delayed. That is the result you demonstrated. Why are we having this discussion?
Now, if you're interested in this and want more detail, I recommend watching 3 Blue 1 Brown's video on this. He does an amazing job at explaining and visualizing this effect that I'm talking about.
So why are you explaining it? Why are you taking the limelight from him? If he does a better job, then let him explain it. Because if you're not so good, then let him, and then don't make noise. Be quiet. I mean, you demonstrated something. I mean, that's good. You should probably stop there. You're just an action lab. I don't mean to detract from your accomplishment, but if you're saying somebody else explains it better, because the way you're explaining it, it doesn't make sense. I don't understand. What's this here? La 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 la. Yeah.
I'll link his video in the description. Also, there are a couple great videos by a channel called Looking Glass Universe, where she tackles this question in depth as well. And thanks for watching another episode of the Action Lab. I hope you learned something. If you did and haven't subscribed to my channel yet, remember to hit.
I mean, this happens to be extremely interesting in the general direction of my research. So that's also good.
That subscribe button, and we'll see you next time.
Very nice, very nice. This video took me a year. Don't know why light slows down in water, part 2. Part 2. Slowing the speed of light down to 2 meters per second. What special relativity feels like? Slow light. I don't get it. I did the double slit experiment at home. Does light slow down in glass? La 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 la. This is an important message, but I'm not taking the phone call. No way. Oh, I can't listen to it. Shoot. Wait a second. Let me shut everything down, because otherwise you're gonna hear it. I don't want you to hear this message. No hearing. Okay, that was good. Good message. Let me send her. Let me send her a message with some emojis, because she doesn't feel well. 1 second. I need more loving emojis. Emojis. No, this one I've used. Let me add flowers. Okay, that's good. La 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 la. All right. So what do we? Which video do we want to take a look at? Resonance, angular momentum, waves. This is light slows down. I want to see his part 2. Let's see if it's relevant.
Hey everybody, today I'm going to be showing you what it would look like if we slowed down the speed limit of the universe to near walking speed. So what would it look like if the speed of light, if it were only about 2 meters per second?
That's not what I wanted. That
I have
is
2 arrows here, face the same direction.
not what I was. Those are not the droids you're looking for, even though it's 4 months ago. This video took me a year. Where's the blue balls? The blue ball, blue 2, blue 3. Why? But why would light slow down? All right, let's try.
I realized recently that I didn't really understand how a prism works, and I suspect most people out there don't either. Arguably, this is one of the most widely recognized physics experiments ever. After all, how many others have earned a place as an iconic album cover? Sure, some of Pink Floyd's design choices run completely contrary to the actual physics, like why did they make the light inside the prism white? And bafflingly, why would you draw all the colors as a discrete set, like a child making a rainbow, despite the fact that one of the key points in Newton's original experiment involving prisms was that sunlight contains a continuous spectrum of colors? Still, setting that aside, it is cool that it's in pop culture at all, and any self-respecting physics enthusiast should know how it works. But the thing I realized is that my understanding hit a wall pretty quickly if pressed. You see, the standard explanation, what you might hear in a high school physics class, for example, goes something like this. When light enters a medium, like glass, it slows down, in the sense that if you look at the crests of the wave, in a vacuum, those crests are traveling at c, the speed of light, but inside the glass, those crests will be traveling a little bit slower. And the specific ratio between the speed of light in a vacuum and the speed inside a medium like this is called the index of refraction for that medium. The reason we use the word refraction instead of, say, the index of slowing is that if a beam of light enters this glass at an angle, then a consequence of this slowdown is that it bends a little bit, or using the lingo, it refracts. And the way my high school physics teacher always explained this was to imagine a tank going from some region where it can travel relatively quickly, like concrete, into something slower, like mud, where if it's coming in at an angle, then as one of its treads hits the slow region first, that tread will be going slower while the other one is faster, causing the whole tank to steer a little bit until that second tread also enters the mud, then it continues straight, just traveling a little slower. We'll get back to the actual reason for bending in a bit, but at this point, the high school physics students typically learn a law known as Snell's law, which specifies exactly how much things bend. If you draw a line perpendicular to the boundary between the glass and water and consider the angle between that perpendicular line and the beam of light, then Snell's law tells us that the sine of this angle divided by the speed of the light.
It's interesting that all over the world, this is what they teach. Instead of teaching, I mean, what's the point? What's the point of teaching these arbitrary physics experiments? I mean, if I'd be teaching, I would just let them do the experiments one by one. Just every experiment from history. If I would teach someone physics, I would go through each and every experiment ever conducted by anyone. One by one, one by one, one by one. Because there are so many simple experiments that blow my mind to this day that it's, I mean, if I knew this all along, it would have simplified my life, maybe.
Light is always a constant. So the slower the light, the lower that angle will be, and that lets you actually calculate how much things refract. What's going on with the prism, then, is that the specific amount that light slows down depends a little bit on its frequency. For example, blue light, which has a relatively high frequency, will get slowed down more aggressively than red light, which has a relatively low frequency. Now, most of the light that you see is not a clean pure sine wave. In particular, the white light coming from the sun is not a clean sine wave. It's something much messier, but it can be expressed as a sum of a bunch of clean sine waves, each one corresponding to a pure spectral color. So when you find
That's interesting. So the prism is actually a Fourier transform.
white light into a prism like this, all those different components get refracted by slightly different amounts, causing this iconic separation of the pure rainbow colors. So that is the standard explanation, and it's not wrong per se, it's just that all of the key components are handed down from on high. Like, why would light slow down like this? And what exactly do we mean by slowing down? And even if you understand that, why would the amount that it slows down have anything to do with the color of the light? Is that just a coincidence, or is it necessary? If you have a sufficiently high standard for explanation, you might go to these facts to feel discovered, rather than feeling like they were handed down. The first explanation I saw that started to give this feeling came from the Feynman lectures on the matter. And a lot of what I'd like to do with this video is simply animate a lot of the key points that he makes there. It involves really digging in to think about each individual wiggling charge in the material, and the propagating light waves caused by each one of those charges, and how all of them superimpose on top of each other, which feels like it should be a complete mess, but it actually works out to be not only understandable, but satisfyingly explanatory. For example, it explains why it has to depend on color, and the key intuition there really comes down to what happens if you're bad at pushing a child on a swing. Bear with me, I promise that'll make sense later. Also, when I mentioned on Patreon the intention to cover this topic, a lot of people had a lot of questions about the index of refraction. For example, numerous people asked about how it's possible for this number to be lower than 1, which really does happen, despite that seeming to imply the impossibility of something traveling faster than the speed of light. There was also a question about birefringence, which is where a material can have two different indices of refraction, causing you to see double when you look through it. And that actually ties in really nicely to putting in the final puzzle piece from the last two videos about the barber pole phenomenon. And a couple people also asked about why light slowing down would imply a bending like this. And I agree that deserves a better explanation than the tank analogy. I promise we will get to all of these questions later, but it makes sense to first lay down some groundwork by spending the bulk of our time on the key question of why passing through a medium would change the speed of a light wave at all. And for this, I want you to think of your material, like glass, as being broken up into a bunch of distinct layers.
Let me see if she saw. Oh, she never saw it. Ta la 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 la.
Ears, all perpendicular to the direction the light is traveling. And we'll start by focusing our attention on the experiment groundwork by spending the bulk of our time on the key question of why passing through a medium would change the speed of a light wave at all. And for this, I want you to think of your material, like glass, as being broken up into a bunch of distinct layers, all perpendicular to the direction the light is traveling. And we'll start by focusing our attention on the effect of just one of those layers on the light wave. The true effect would be
So layers. He's gonna think about the layers.
minuscule, but if you'll let me exaggerate it for a moment, what it does is kick back the phase of the wave. And maybe it's worth a brief aside to make sure we're all on the same page when it comes to wave terminology. If you go and graph the function sine of x, when you put some term in front of it, affecting how high that wave oscillates up and down, that's what we call the
He's using the same website that I use for drawing graphs.
amplitude. When you put a term in front of x, this will affect how rapidly it oscillates. If this is meant to describe a wave over time, that term would be called the angular frequency, whereas if it's meant to describe a wave over space, that constant would be called the wave number. Then if you were to add some other constant inside that sine function, and notice how as you change what that constant is, it sort of slides the wave left and right, that term describes the phase of the wave. So when I say that our light wave...
This is great. Next time I want to analyze a wave equation, that's what I'll do. That's because every time I have to rethink it, it's really convenient.
causes its phase to get kicked back. I mean, if you take whatever function describes it before it hits the glass, then the function describing it after that looks almost the same, just with a little extra something added to the input of that sine function. Like I said, in reality, that'll be a very small number, something proportional to the infinitesimal thickness of that layer. So I'll keep drawing it as something exaggerated and keep track of the value of that phase kick over here on the left. Let's say you go and add a bunch of other layers of the glass, each one also applying their own kickback to the phase of the wave. The question for you is, what does that new wave look like? If the value of that phase kick applied by each layer is something really close to zero, then the wave is hardly affected at all. But the larger that phase kick, the more the wave kind of gets squished together among all those layers. Admittedly, right here it looks all kaleidoscopic and weird, but that's really just because I have a discrete set of layers, each applying an unrealistically large kick. Notice what happens if I smooth it out by doubling the density of layers, but having each one only apply half the phase kick.
Wow, that's great. I mean, it's good because animations, I believe animations are just mathematical equations. They're obviously easier to understand. Like when they teach you math, really they should teach you geometry, and today they should teach you animations. You can learn from the animations just as much as, much more, I would say, than from the mathematical equations.
And then I do that again.
Because at the end of the day, mathematical equations or physics phenomenon, I need to imagine them. So it's obviously easier if somebody shows me a simulation than me having to think up the details of a simulation.
Again, I double the density of the layers, but have each one only apply half the phase kick. As I continue this over and over, approaching a situation where you have a continuum of glass, each layer applying just a tiny infinitesimal phase kick, what you end up with is identical to, indistinguishable from, a wave that's simply traveling slower, oscillating up and down with the same frequency, but with a wavelength that's been kind of scrunched up. This right here is the first key idea with the index of refraction. Instead of asking, why does light slow down in glass, what we really need to ask is, why does its interaction with a single layer of that glass cause a kickback to the phase of the wave? And then when we want to get quantitative and understand exactly how much the light slows down, which is critical for understanding why it depends on color, instead the real question is, how strong is that phase kick? From here, it's helpful to turn back to the fundamentals of what light even is. This is something we talked a lot about in the last video, but a little review never hurts, so let me go over the essentials. As many of you know, light is a wave in the electromagnetic field, but here we'll just be drawing the electric field. The electric field associates each point in 3D space with a little free...
This is genius. I mean, and this is, I mean, the question is, are there computer simulations, like free off the shelf vector computer simulations that you can just, you know, either run yourself or someone has run before and recorded for what an electromagnetic wave is and stuff like that. And that will, that is so crucial because no one imagines, no one I've seen imagines or shows what a electromagnetic wave looks like. Just looking at the equation, whatever they show is a cross section of a cross section of what it should look like, but they never show the full 3D view. I don't know why.
Three-dimensional vector telling you what force would be applied to a hypothetical unit charge sitting at that point in space.
That's genius. That's exactly what a field is.
The key thing going on with light is that if you have a charged particle and something causes it to wiggle up and down...
Let me review the
So let me
definition.
go over the essentials. As many of you know,
I just wanted you to hear his definition of what a field is.
light is a wave in the electromagnetic field, but here we'll just be drawing the electric field. The electric field associates each point in 3D space with a little three-dimensional vector telling you what force would be applied to a hypothetical unit charge sitting at that point in space. The key thing going on with light is that if you have a charged particle and something causes it to wiggle up and down, that results in these propagating ripples in the electric field away from the charge.
That's genius. And he's only showing the electro field, not the magnetic field. Let's watch it again. I wish he would show more of it.
Going on with light is that if you have a charged particle and something causes it to wiggle up and down, that results in these propagating ripples in the electric field away.
And that's only two-dimensional. Really, it's three-dimensional. And does it interact with the magnetic field? I don't know. Does it? I don't know.
From the charge, and that propagation is traveling at the speed c, the speed of light.
Good. So these are electric waves traveling at the speed of light. This is the ether, by the way. Now we're looking at the ether. This is the ether jiggling, which is what this video is about. This video is about a new method that I am coming up with of proving the ether wind. So this is good. These are the ether waves, the electric waves. Very nice.
those ripples happen to reach another charged particle, they cause it to wiggle up and down, albeit a little more weakly than the initial wiggle, and that in turn causes its own propagations. The way we described this in the last video was that if at some point in time a charge is accelerating, and after a little delay, which depends on the speed c, the existence of that acceleration induces a force on another charge. We went over the specific force law describing this. It's something that can be derived downstream of Maxwell's equations. But for our purposes here, the main thing to tuck away in your mind is that the amount of time it takes that initial acceleration to cause any kind of influence elsewhere travels at exactly the speed c. And really, you should think of c not so much as the speed of light per se, but as the speed of causality. It determines how fast any kind of influence travels. It's just that one of multiple.
That's ridiculous. Causality. It's the speed of propagation of waves in the ether. That's all it is. And the ether is a very real fluid that is flowing through us right now, and we're waving through it right now. And it all fits perfectly together. It's described very well by general relativity and quantum field theory. And it's really very simple. And special relativity becomes just wave mechanics with relativity. So relativity is that the effect of relativity is real, but it's in respect to the ether, to the so-called absolute ether. And when two people are moving relative to each other, that's really irrelevant. They're just moving relative to the ether. And the effect that they're seeing of each other, that's because each one is moving relative to the ether. And the effect is real, because it's like in the rubber ducky. The rubber ducky's clock is really slowing down. It is really slowing down, where the word really means in reference to the ether. That's how I would define it. The universe is filled with this ether fluid, and it keeps refilling through the dark energy, which we need to write a paper about.
Multiple consequences of that.
It has nothing to do with the quantum fluctuations. The quantum fluctuations are the effect of the ether. The ether is always vibrating, but new ether is coming into existence and is creating a positive pressure, causing the universe to expand. This is not, the expansion of the universe is not caused by the quantum fluctuations. The quantum fluctuations is what the ether does, but there's no positive pressure created by the quantum fluctuations. There's no positive pressure there's no pressure created by the fluctuations. Waves do not apply pressure. The waves happen in every direction simultaneously. There's no pressure. So that's not causing the universe to expand. The pressure is from new ether being created and the old ether being annihilated by massive objects. But there is an imbalance. But we'll come back to this. We need to write a paper about that. Anyway, so we're talking about electric waves. Very nice. The way he says it's causality, that's nonsense. That's absolute nonsense. This equation should be pretty straightforward. It's just the electric field. This is what he's showing. What he's showing is what it says here. He's running this simulation in his simulator. So he gave the simulator, he's asking the simulator to show blue arrows. That's the electric field in radians. I guess radians? Radial? I don't know. It's a radial cross section. So R is the distance from the source, and T, so it's negative Q. That's the source. The test element doesn't matter what its charge is, divided by 4 pi epsilon naught. Why is there a c squared? This is that's interesting. 1 second. This is the electric wave equation. No, it's not. So what is that? So when this moves up and down, so let's say we have a test. Let's say we have this arrow. We want to see what happens to it. So what is A? Okay, he doesn't explain this equation, so I don't know what he means. What is A? Maybe A is the acceleration? No. Oh, the acceleration of the object. So the acceleration of the object, I don't know why it says perpendicular. The acceleration of the object is a function. I don't know. Anyway, it's a simulation, so we can figure it out. So he's moving this up and down, and so the test particle is probably negative. Let's see. If the test particle would be very close, let me see.
It is the speed of light. In particular, when you get a charge oscillating up and
Is he showing this is the direction of the electric field, but it should always be in the, like, it should be in the direction, it should be in the direction of the, oh, it's positive. Anyway, it should be in the direction of the particle. All the arrows should be pointing at this particle. Why are they? I think these are what he's showing is the changes. He's not showing the direction of the field. But it says here, this is the electric field. But that's not the direction of the electric field. The electric field, yes, the electric field is actually not in the direction. It's not in the direction. That's what they always show. When it's wiggling up and down, the waves created move up and down. And that's what we're seeing here. That is actually something that always bothered me. Why does this equation cause an up and down electric field? So what ends up happening is that an electric test particle would move up and down, and that is what we want. That is what we want. But also, shouldn't it be moving towards or away from? So we're assuming it can't. It's stationary. It can't be moving towards or away from. Or we're looking only at the effect in the perpendicular direction. We're ignoring the pull and push. I don't know. I mean, if this charge would not be moving and we would have a test particle over here, the test particle, if it's positive, well, it's negative, so it's being pulled. It's in the direction of negative r. So if this is r, it's in the negative direction. I think it's towards. So we're assuming a negative test particle. Anyway, the test particle should always, there should always be a component pulling it towards. I don't know why it's only up and down. A test particle should always be, if it's negative, should be attracted towards this positive particle. So I don't know. Maybe that's why it says here we're only interested in the up and down vector. The removing r, so this ends up being the vector that we care for. So we're only looking at, so we're assuming it's a stationary test particle, we're not letting it move. Okay. Because we're just taking the absolute value of this vector and the absolute value of this vector, so we're losing all the vectors. So the only vector we have is A, and that's just this motion. So we're just taking this motion, this vector, so this vector. That's why it's red. So that's why it's red and blue. So this vector, the red vector, so if we look at any test particle, so at time t, this is the vector. It's the acceleration, because all we care for is the acceleration of the charge of Q. So we're accelerating at time t. Now r is where the test particle is located. And c is the propagation, is the speed of propagation of the wave. So whatever this vector is, whatever the distance is, so distance over the speed should give us the time. Distance over speed, speed times time is the distance, I think, right? So distance over speed, speed is distance over speed. So distance, distance over time. So distance over time, distance over time. Distance divided by distance over time is just time. Okay. So this is time, which means whatever it is at time t, later on, somehow, because we're subtracting, it means later on. Later on, we'll have this effect over here with this constant divided by r, so it gets reduced by r, but it should be different for different angles. Where's the angle? Where's the angle? This is for any r. That's not, you can see it's not true. It's not radial. Over here, it's different. Nothing happens over here. There's no effect over here. So that doesn't make it. It can't be only r. There needs to be a theta. It should be different. The effect is perpendicular. So the effect here is 0. Because what does it mean perpendicular? So he's taking this vector. So over here you get the full effect, but it's divided by r, so it gets weaker. But if you go over here, there's no effect because it's not perpendicular. So you need to have it perpendicular. So perpendicular means the cosine. So it's the acceleration, it's this vector cosine. So I think this means the cosine of this vector. Wherever it's, but he's not multiplying it. There's no a times r. He's doing the absolute value of r. So this is a times r hat, a unit value. That's what it means. This is the vector a dot r unit. So that he's only getting wherever the test particle is. So for here, it's multiplied. Yeah, it's multiplied by a unit, so it doesn't change the value, but it's 0. Okay, that would give you 0 over here. So a perpendicular just means a dot unit r, or a dot r hat. R hat is the unit in the unit vector in the r vector direction. So this guy over here, so r unit, r hat would be in that direction, but it would be tiny. And this dot, this, right? Dot. Let's say this place. So let's say this is r hat. So r hat cosine this is 0, and that's why along this line it's always 0. Okay, that's a perpendicular, but he doesn't explain any of this. He really needs to. He is a math channel. He should really explain this.
And down in a nice clean sinusoidal motion, you can think of these rippling effects in the electric field as describing the force that would be applied.
This is three-dimensional. This is amazing. So this is the same equation in 3 dimensions. So every cross section is the same as the previous animation.
To another charge sitting there as a result of that past acceleration.
It's not really 3-dimensional because there's these layers. These are fake. So he removed a lot of the test particles because it would be very difficult to understand what's going on.
Will freely admit that I had a bit too much fun in that video just simulating how the electric field responds to accelerating charges, that I'm kind of doing the same thing here. But there are two important facts for our pursuit of the index of refraction. The first is that when you have multiple different charges oscillating up and down, the net effect on the electric field is just the sum of what it would be for each individual charge, which is kind of what you would expect. And then the way that it shakes out is that if you have a row of charges oscillating in sync with each other, or for our purposes today, a plane of charges, all wiggling up and down in sync within that plane, then the effects of each individual charge tend to cancel each other out in most directions, except perpendicular to that plane, they actually constructively interfere. This is how you can get a concentrated beam of light. That's the important thing. If you have a layer of charges wiggling up and down in sync with each other, then even far away from that layer, it produces this nice sinusoidal wave in the electric field that we're so fond of drawing to represent light. When I draw
So he says, so let's understand how he understands it. So he's taking a cross section of the X. So it's an infinite, he's assuming it's an infinite plane. So if you have an infinite plane moving up and down, that's when you get these perfect
actually constructively interfere. This is how you can
waves.
get a beam of light. That's the important thing. If you have a layer of charges wiggling up and down in sync with each other, then even
so an infinite plane moving up and down would give you these perfect. Now I understand what they mean. Oh my God! After years of not understanding why they draw these waves like this, because in my mind they're shaking a single electron, a single charge up and down, which would give you something much more really complicated. But if you have a plane moving up and down, yeah, then you get these. This would be a cross section of the wave that's created. That's nice.
far away from that layer, it produces this nice sinusoidal wave in the electric field that we're so fond of drawing to represent light. When I draw a light wave like this, it's really only depicting the electric field on a single one-dimensional line. A more full picture of light in 3 dimensions would look something more like this. That tends to be a little bit busier, so usually we just draw the sine wave. So, thinking back to the question of why interactions with a layer of material would cause a kickback to the phase of the wave, let's start thinking it through. When a light beam enters a material, like glass, then it causes all of the charges inside that material, electrons or maybe the occasional ion, to wiggle up and down in response to that light wave. You might think that adding together all the propagations of all the charges, think about it one layer at a time. As the light wave causes this layer to wiggle up and down, that wiggling produces its own second-order light wave.
Okay, so this layer wants to wiggle up and down. Why? Let me drink some water. Well, that's basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So when this particle moves up and down, it causes a test particle here to move up and down. So if a wall of electrons are moving up and down, it would cause a wall of electrons here to move up and down. So it's just causing the electrons to move up and down a little bit. My heart still hurts. La 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 la. I met someone. We had a really good first date. She's really nice, really nice, really nice. Tall. I love tall chicks. Anyway, let's kill ourselves. It's time to die. All right. So that's the way it is. Finally, I'm beginning to understand how people express not animations, but when they say, "Oh, it's a sine wave, it's a whatever wave." Now I understand why they say it, because they're not imagining a single electron moving up and down or a single charge moving up and down. Rather, they're assuming it's a wall. It's an infinite wall of electrons moving up and down. That's perfect. Then it simplifies everything. Okay, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. So this is the wall of electrons that is being affected. So a whole cross section is moving up and down. But that's because light comes in parallel. When it comes, especially if it comes in from the sun, by the time it comes to us, it's already completely, for all practical purposes, it's parallel. And that's why whatever it impacts on, it's a complete. You can imagine a perfect wall of electrons being influenced simultaneously, moving up and down
at the same frequency. And it propagates in both directions perpendicular to that layer. The overall electric field then looks like the initial incoming light wave added together with the second order wave. By far the most distracting part of what's going on here is everything on the left, and this actually corresponds to the light being reflected back. And from experience, you all know that when you look at water or you look at glass, light not only goes through it, but some of it gets reflected back.
Okay. So these electrons, they move up and down because of the incoming waves. But as they move up and down because of the incoming waves, they create themselves waves up and down, going going to the right and to the left, both directions. So what is he saying here?
And we could have a whole interesting discussion on quantifying exactly how much, but in the spirit of staying focused, we will completely ignore that for today and only focus on what's happening to the right of that layer. You can probably predict what I'm going to say. It turns out that when you add that second order oscillation, the overall effect is almost identical to the incoming light, but just shifted back in phase by a little bit. And then because many successive shifts to the phase like this are the same thing as light slope.
So this is the reason you get the delay, a tiny delay from this wall. Really, what I would say, you don't need to even go so far as to add two waves, because then you have to prove it, and it's a difficult proof, because you need to do a mathematical proof. What you really need to say is that the electrons, because they have inertia, they have momentum, therefore their waving cannot be at the speed of light, because they have a mass. So they need to move a little bit slower. They need to react a little bit slower. They're always reacting a little bit slower. Whatever the incoming information is, the electrons are reacting a little bit slower. But he's saying, no, that's the outgoing wave. The initial wave keeps going normally. Their output is slower. Is it? Because these guys are waving not at the right speed. So as this is going down, these guys are a little bit behind. So these guys are slowing down this wave, and forever will they slow down this wave, just a little bit. So the red is always in front of the blue. The blue is always a little bit behind. It's a little phase shift. This is called a phase shift. It's not that the frequency is not different. It's not different frequency. It's just a delayed response, because the electrons have a little bit of mass, so they're a little bit less reactive than the original waves. That's fine. So what you're getting is, so the overall, so this plus this, he didn't do the complete addition, but really what you're getting is that the red has shifted a little bit to the back. So the red has slowed down a little bit after influencing the first wall. So the red, which here is yellow, has shifted back just a little bit, and I guess the distance between these two lines is two planes. During this one, the red has shifted back, has been delayed a little bit. The speed of light has slowed down a little bit in here. Now, if we didn't have any more layers, then the effect of the first plane would disappear, but the red would continue as before, and that's why the speed of light would go back to normal. That is what happens as it leaves. As it leaves, it goes back to the normal speed of light. Let's see what he says.
Slowing down, this will ultimately explain the index of refraction. But of course, the sufficiently curious viewers will now be raising their hands and asking, why is that the effect when you add them together? And so here might be worth a little sidebar on how to think about adding two waves together. If you draw some sine wave with some particular amplitude, some specific...
I thought that you explained it. At least I explained it. So what? Now what?
Specific frequency and some specific phase, and then you draw another sine wave, also with its own amplitude, frequency, and phase. In general, it's very hard to think about what the sum of those two waves should look like as you tweak those initial parameters. In the specific case where the frequencies are the same, which is true for our example, the result will also look like a sine wave with that same frequency. But even then, it's a little tricky to think about exactly how to describe that wave. It has some amplitude and some phase, and if I ask you to concretely compute both of those numbers based on the amplitudes and phases of the initial waves, it's not immediately clear how you would do that without maybe throwing a bunch of trig identities at the problem. But here's a really nice way to think about it. Imagine that first wave describes the y component of some rotating vector.
Oh my God, he's so he always uses these rotating things.
The length of that vector corresponds with the amplitude of our wave, and then the initial rotation of that vector corresponds with the phase of our wave. And then similarly think of that second wave as describing the y component of another rotating vector, where again the amplitude corresponds with the length of that vector, and the phase of the wave tells us the initial angle of that vector.
It's going to be a little bit behind.
Just think about adding those two vectors tip to tail, and because they both have the same frequency, as both of them rotate, their sum kind of rotates in lockstep with them. So
that's very good. That's good. So blue, yellow, and green. Let me get rid of this. So the blue and the yellow, you get the green, and the green ends up being delayed. Yeah.
If you want to think about the amplitude of a resulting wave, it comes down to the length of this vector sum, and similarly the phase corresponds to
well, cannot be bigger than the original.
The angle of that vector sum. In some cases, this tells you things that you probably already knew. Like if the two phases happen to be the same, then you get constructive interference and you have a bigger wave that results. And if the phases were 180 degrees out of sync, then you get deconstructive interference with a relatively small resulting wave. What's a little bit less obvious, but what's crucial for our discussion here, is that if the phase of that second wave happens to be exactly 90 degrees behind the phase of the first, so kind of a quarter cycle out of sync, and if that second wave is also very small compared to the first, then if you look at the little vector sum on the lower left, you'll notice how this means that the resulting wave is almost identical.
That's good. So it's exactly 90 degrees. So it's always opposite. The original, when this goes up, this goes down, that would be opposite. So it's 90 degrees. Why is it 90 degrees?
Identical to the initial wave, but just shifted back in its phase by a tiny bit. Moreover, the size of that phase shift depends on the specific amplitude of that second wave. So looking back at our previous animation, where we have some wiggling charges in a layer of glass causing these second order propagations that need to be added together with the incoming light, the way it works out is that the phase of that second wave is exactly
oh my God, I'm falling asleep. These things are so boring.
quarter of a cycle behind.
And I don't need it. I mean, all I need to know is how she slowed. Let me see how long we've been here. 52 minutes. Professor Howe, Dr. Howe, how did she slow down light as much as she wants? Like, I think she froze a crystal. Maybe frozen glass. Maybe really frozen glass slows down significantly, even more than just glass.
Into the phase of the first. So when you add them together, you get this little phase shift. And then, critically, the size of that phase shift is bigger when that second order wave is larger, and then smaller when that second order wave is smaller. Again, the very curious viewers will be raising their hands and saying, why does it work out to be exactly a quarter of a cycle behind? There is a
That's the question. Why is it exactly 90 degrees behind?
very nice reason, but it's just a little too much detail for us today. If you're curious, I highly encourage you to take a look at the Feynman lectures on the matter. For our purposes, step back for a second and think about what you need to explain the
Feynman lectures, oh my God. It's good that he gave these lectures. It's bad that he taught bad philosophy of science. That it's very bad philosophy of science.
the key question of prisms, which is why the index of refraction would depend on color at all. As you now know, that index depends on how much each layer of glass kicks back the phase of the wave, and that phase kick depends on the strength of the second order wave resulting from charge oscillation in a layer of that glass. So you need to drill in and understand exactly how much those charges wiggle in response to an incoming light wave. So let's zoom in on that layer and think of each one of those charged particles, and even though the specific molecular structure is going to be something very complicated, we're going to model each one of those charges as if it was bound to some equilibrium position by a spring, or maybe a set of springs. I don't mean this literally, of course, I just mean if we describe the displacement of this charge from its equilibrium.
That's actually pretty much how the ether works. Maybe there's more complex springs, but basically it's a fluid. It seems to be a simple fluid with simple particles that make it up. It's just that they're out of our dimension. I honestly, I don't know how we can ever interact with these particles, because we ourselves are waves in this fluid. How could we ever, like when we build particle accelerators, we're accelerating particles that are actually waves in the ether. But how do you cause the ether to break? How do you break the ether? I don't know. I don't know how you break the ether. How do you like, what kind of particle accelerator would you use to collide ether with ether? How would you accelerate ether? The only way I know to accelerate the ether is through gravity. Gravity, yeah. But how do you get, it's like you need two planets to drag in. It's like, I don't know. I don't know. I mean, right now, the ether is flowing into me right now. It's crashing into me and it's getting annihilated. But it doesn't seem to leave behind any marks except for inertia. It's giving me inertia while colliding with me and self-destructing. It's giving up its life to give me inertia. And mass, well, same thing, gravitational mass and inertia. I don't know. Anyway, yeah, but it's basically, he says it's not, it basically is, there's no springs, maybe. I don't know, there might be, who knows. I don't know, there might be simple forces between these particles. I don't know, but no one is researching this. I'm the only one even thinking about it. I don't know what to do. So I'm trying to think of what the ether is. Well, at least now we're coming up with this new method to discover the ether. This should wake up the scientific community maybe a little bit. Anyway, let's keep going.
Little vector x that's going to depend on time.
Let's see what's going on. Is anyone talking to us anywhere? No, no one is talking to us. No one cares. No one cares.
Then in our model, the force applied to the charge, pulling it back to that equilibrium, is going to be something proportional to the size of that displacement, with a little proportionality constant k. This is the same law that governs how springs work. You might ask if that's accurate. And the idea is that for very small displacements, it's actually a really good approximation. This is a very common thing to do throughout physics. We would call it a linear restoring force. The idea is that maybe the actual force law depends on the position in a much more complicated way, but we're basically taking a low-order approximation near the equilibrium. If I just run this as a simulation, plugging in this force law, here's what that displacement looks like as a function of time. What you get looks like a sine wave. This is called simple harmonic motion. And the frequency of this wave is going to matter a lot for you and me. And that comes down to solving this differential equation. Because the force is really the same thing as mass times acceleration, and the acceleration is the same thing as the second derivative of that displacement. So what we're saying is we want some function whose second derivative looks like a certain constant times that function itself. Any differential equation students among you might enjoy thinking about how you solve this. I won't go over the full details, but the answer is reasonably intuitive, and anyone who knows a little calculus can just check it for themselves. The way it shakes out is that the initial condition is that our little charge has a velocity of 0, but it's offset from the equilibrium by a little vector x naught. Then the way it evolves over time looks like x naught multiplied by a cosine expression. So the amplitude of this wave is kind of uninteresting. It just depends on how far we pull things back originally. But the meat is this frequency, square root of k divided by m. And if you think about it, this should hopefully be at least a little intuitive. For example, if you increase k, which is kind of like increasing the strength of that spring, then it results in a faster oscillation. Whereas if you increase m, the mass of the particle, there's a lot more inertia, and it results in a slower oscillation. This term, square root of k divided by m, has a special...
So from the speed of light, we should be able to at least discover k over m. If we assume k over m, that's interesting. So we can, and we need to assume, we can assume k over m. That would be interesting. Whatever springiness the ether has, the ether particle has, we should be able to discover it. If we just assume, but that's, I think that is exactly, the speed of light comes out of the permeability times the permittivity or something, or 1 over the square root of these two combined. But that is, I don't know, but it's a good topic to model the ether with springs, with a spring constant, and to come up with, at least with the k over m. At least we'll know the ratio of k to m. What I mean can't be massless. If it's massless, then the speed of light would be infinite.
Name, it's called the resonant frequency for our simple harmonic oscillator. And being a little more precise, I should call this the resonant angular frequency. This is always a little bit of an awkwardness with physics where whenever you have some kind of cyclic process, when you give an intuitive description, it's natural to phrase things in terms of the frequency, the number of cycles that this process makes per unit time. But when doing math, it's often more natural to talk about the angular frequency, which you can think of as describing how much angle this process covers in radians per unit time. It's just the same as the frequency, but multiplied by 2 pi. So for example, if you have something like a cosine expression, which you might think of as describing the x component of a cycling vector like this, then the term sitting right in front of the t in that cosine is the angular frequency. This is why angular frequency makes the math a little cleaner. For example, in our simple harmonic motion, the term sitting in front of p looks like the square root of k divided by m, which I'm writing as omega sub r. Let's package all of that up and call that our solution in the simple case where there's
I'm trying to think if the speed of light it has nothing to do with the frequency of the light itself. The speed of light is the speed of propagation. That has nothing to do with this wiggle. This wiggle is just a simple harmonic oscillator.
There's no external force acting on our charged particle. But of course, what we're interested in is what happens when you shine a beam of light on this material, which intuitively causes this charge to jiggle, but the question is how much. In our equation, this looks like adding a new force term corresponding to the light wave. That force oscillates up and down.
Wait, that's interesting. He's actually modeling the ether. Isn't he? Force is equal to... What is going on here? The K, but there's no M. So this is the springiness based on the displacement. Force from a light wave. This is the force. But F is supposed to equal to MA, but there's no M. So, I don't know.
Also, according to some kind of cosine function, but this time with a distinct angular frequency that I'm going to call omega sub L. E naught here describes the strength of the wave, and then Q describes the charge of whatever.
Wait, omega he said already contains K over M.
For particle we're modeling. As usual, it's a lot easier to think about when we only draw a subset of that light wave, and in this case, we're going to draw it on the plane of the layer of material that we care about. You might think of gusts of wind blowing our little ball on the spring up and down in a clean sinusoidal pattern. Or, as another analogy, it's similar to pushing a child on a swing. The swing would oscillate on its own due to the force of gravity, but you, as the pusher, are applying an external force, which itself is oscillating over time. Although a key difference here is that the frequency of that external force, in general, has nothing to do with the resonant frequency of that little oscillator. The better analogy would be if you're pushing the child on the swing with a cyclic force that has nothing to do with what the swing naturally wants to do. And my favorite part in literally trying to do this with my niece is that at some point she gently murmurs to herself, "This isn't home."
What do you mean your niece? So you don't have any children?
Mom does it. Now, in trying to understand how much our charge is oscillating in response to the incoming light, let me start by just simulating it and plotting the result. You'll notice that there's a little startup period where it kind of has to get going, but then after that, mercifully, it looks nice and clean, just like another sine wave.
But is he describing the motion of an electron, a test particle, or an ether particle?
Now, you might be thinking, yeah, everything is sine waves, but it's important to understand that this one has a very different character from the sine wave we saw earlier. Earlier, without any external forces, the frequency of that wave came down to the spring constant and the mass, which is to say, it depends exclusively on material properties of the glass. By contrast, with this external cycling driving...
Oh, it's the actual particle of the glass? The nucleus of a glass atom or whatever?
The frequency in that steady state is the same as the frequency of the light. And then in our first case, the amplitude of the wave was kind of uninteresting. It just depends on how far you pulled the string out to begin with. But in the second case, the amplitude of this wave is actually where all the interesting stuff happens. Exactly how much will this charge be oscillating in response to the light wave? Again, I won't go over the full details of solving this, but any eager calculus students among you might enjoy going through the exercise where if you just guess that a solution looks like a cosine wave with the same frequency as the light and you solve for the amplitude, you can get a concrete solution to this equation that looks like this. This is worth unpacking for a bit, and just to be clear, this is only describing things in the steady state, after things have kind of gotten up and going. A full descriptive solution would be notably more complicated. As I said, everything interesting here comes down to the amplitude, which here looks like a large collection of constants, most of which should be pretty intuitive if you take a moment to think about it. For example, it is proportional to the strength of that incoming light wave, so the stronger the light, the more the oscillations. It's also proportional to the charge, which again makes sense. And the real heart of the matter comes down to what's sitting in the denominator here, the difference between the square of the resonant frequency and the square of the light frequency. And to build a little intuition, take a moment to think about what would happen if the frequency of the incoming light was something very close to the
Where's the mass?
resonant frequency of this oscillator. This is analogous to the normal situation pushing a child on a swing, where the frequency of your force lines up quite closely with what the swing wants to do. In this case, running the simulation, notice how the oscillations of that particle will grow and grow and grow, becoming quite large over time. Some of you may know the famous example of the Millennium Bridge in London, where on its opening day, it started oscillating way more than the engineers expected it to. And what was going on is that the frequency of the steps of the crowd lined up very closely with a resonant frequency, causing this worryingly high amplitude. By contrast, notice what happens in the simulation if the frequency of the...
Yeah, because people are biofeedbacks, literal biofeedbacks. I think that's what caused it. The people felt And initially, when you walk on the bridge, you notice it, but you don't notice it. It's subconsciously you notice the shaking, and you step with the shake. You don't notice that you're stepping with the shake. So you're adding just a little bit. You're resonating with the bridge. That's the nature of your brain. You resonate with the input, and that's what happened.
The light, omega sub
I'm assuming. I don't know.
L, is something much smaller than the resonant frequency. For this particular simulation, it takes a little bit of a moment before things get into their full swing. Eventually, it finds a nice sinusoidal motion, but the amplitude of that motion is much more modest in comparison. So what our equation is telling us is that the larger the difference between those frequencies, then the bigger the denominator, so the smaller the overall wiggle to that charge. And again, this is something you can see in the footage with my niece. As I'm applying a force with a frequency that's very different from what the swing wants to do, she ends up oscillating at the same frequency as my force, but she's going at a relatively low amplitude. Stepping back.
So she's enjoying it. He's making sure that we know she
So the
loves
smaller the
it.
overall
Let me
wiggle to that
see.
charge. And again, this is something you can see in the footage with my niece. As I'm applying a force with a frequency that's very
I promise she enjoyed this.
different from what the swing wants to do, she ends up oscillating at
Do it again, were her exact words.
the same frequency as my force, but she's going at a relatively low amplitude.
1 second. Let me
Very
see.
different from what the swing wants to do. She ends up oscillating at the same frequency as my force, but she's going at a relatively low amplitude.
To all the sticklers, yeah, I know the way I'm holding the swing affects the length, and so changes the resonant frequency. Okay.
Stepping back, what this means is that as you shine light into a material, like glass, it's not just that it induces wiggles in the charges of that material, but the specific size of those wiggles depends on the frequency of the light as a consequence of this denominator term. And the more those wiggle, the bigger the size of the second order wave caused by that layer, which in turn causes a bigger shift to the phase of the overall wave. Because a lot of different shifts to the phase are what causes this apparent slowdown to the light, it means that the amount that it will slow down ultimately depends on the frequency of the light. So that is the real reason why prisms work. You cannot truly explain the light separation until you get down to the driven harmonic oscillator. Now, I have left out a number of...
I don't get it. Why did he not discuss the mass? Why is he ignoring the mass? I guess he just wants to show that there's a difference in the omegas. There will be many resonant frequencies of, I don't know.
details. And again, I encourage the curious viewers to take a look to find them much
This is good stuff. I need to come back to this one day.
that a lot of this is based on. One quite important detail that would be a little criminal not to mention is that when we're modeling our charge as a little harmonic oscillator with this linear restoring force, there should really also be a term that depends on the velocity of that charge. You might think of this as a kind of drag force. This term accounts for the fact that energy from the incoming light wave is absorbed by the material. Without it, this whole explanation would seem to imply that
Yeah, it heats up.
light always passes through every material, not just glass and water, when, as you can tell just by looking around, there's all sorts of materials for which light is mostly reflected and absorbed. As I mentioned at the start, folks on Patreon had numerous questions about the index of refraction, like how it can be less than 1 and why slowing implies bending, so I made a supplemental video answering a handful of those questions, which should be published in just a few days. In the meantime, my friend Mithina from the channel Looking Glass Universe just put out a
Mitina.
There were videos on the related but definitely distinct question of whether light slows down in a medium, not in the sense of following the crests of a clean, pure sine wave in a steady state, but in the sense of trying to send information through that medium, like with a little wave packet. I definitely owe the existence of this video to many conversations with her about this topic, and viewers here will definitely enjoy taking a look, especially at the second one. By the way, some collaborators and I made this notebook that I think a lot of viewers might enjoy, and given that it's the holiday season, it seems worth a quick mention. The premise is that every one of the pages has a quote that's related to math, and I had a lot of fun curating them all, trying to constrain myself to quotes conveying some genuinely thought-provoking idea. And then aside from the content, I basically...
Oh, that's very nice. So it's a notebook that you can use, but it has quotes from great mathematicians.
Made the kind of notebook that I most enjoy taking notes in, something that's readily portable with very faint grid lines helpful for diagrams, but otherwise unobtrusive, all bound in this
He never has corrections? How's that possible?
nice soft faux leather. If that seems up your alley, you can find them in the 3 Blue 1 Brown store next to a lot of other mathematical merchandise.
Oh my god, Jesus, please save my life! Oh my god. How's the audio? I hope it's good. Oh my god, Jesus, please save my
Really
life!
understand how a prism works, and I suspect most people
Oh my god. How's the audio? I hope it's good. Oh my god, Jesus, please save my life! I think the audio is okay. Let me check. Is the audio correct? But is the audio correct? This looks correct. Also, does this look correct? Oh my god, la 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 la. Okay, the input is USB and the speaker is the headset. That's good. Echo cancellation. All right. So in one day, my mic banana headset died, and the USB next to it mic died. Not died, but my Brave browser decided to block. And I gave up. I didn't know what else to do. I ended up switching the USB connector, and then it started working. So my mouse is now connected. Anyway, it's a complete mess. I don't know what to do anymore. Okay, but all of this is irrelevant. I just want to know. Okay, now we know the theory why light slows down, but I need to know how to slow down light significantly. I need to see how's, like this guy, he said that how Professor Dr. Howe was able to slow down light to full stop. How did she do that? Slow light. How? Half-life. No, not half-life. Oh my god, why am I so tired? What? Oh, we have a good message. Let me see the message. She's still not sleeping? Oh my god. La 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 la. All right. Okay, what are we looking for? Professor Howe, slow light. What else should I say? Dr. Howe? No. Oh my god. What do you want me to say? I don't know what to say. Dr. Howe slows light. How much was it? 15 meters per second or something. Oh, physical. Lena Howe was able. Okay, there it is.
To slow down light. In 1999, Harvard physicist Lena Howe was able to slow down light to
Oh my god. So she was probably like 50 then. So she's 75 now.
17 meters per second. In 2001, she was able to stop light completely. Since then, she has continued her work with light at Harvard University. In her latest experiment, she not only stopped the light but also moved it around, manipulating it for half a minute, before she made it reappear. In 1999, Harvard physicist Lena Howe was able to slow down light to 17 meters.
17.
In 1999, Harvard...
Shut up. Using Beck. What is BEC? Danish scientist. Why is it only shorts?
At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level.
Why? It's so easy to remove these moles, and they could be cancers, but they look awful. Why don't people remove them? It's basically free. You can do it yourself.
Well, that was just absolutely fascinating.
Especially like Norwegians and a lot of Eastern European women have these. Like you can see a beautiful model, unbelievable perfection. And then she has all these moles on her body that could be so easily removed. Oh my god. I need to go grab something to eat. I'm becoming hungry.
Bose-Einstein condensate to carry out her experiment.
Wait, she uses an Einstein Bose condensate?
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment.
What is a Bose-Einstein condensate? I remember hearing a lot about it. That's where a boson comes from. It's not from Boson the clown. It comes from Bose.
She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium, and the front edge enters first, and it's still in free space. That'll catch up, and that'll create that compression, and it'll end up being compressed from 1 to 2 miles down to 0.001 micron or even smaller than that. You could say, well, gee, it needs to stop light because I would just send a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it's turned into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and we can move on.
Yeah, it's lossless. It's a lossless interaction.
One day, ultra-cold atoms will probably be used to store any...
Oh, it's ultra cold atoms. So she's using ultra cold atoms. So maybe we could use it, but I think it's going to be okay. It's one way to run our experiment.
to process information. Even now, cold atoms are being turned into prototype quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool, it's fun, and we can do it.
Oh my God! Why don't you get a haircut?
Right? I mean, we actually can take atoms.
This guy, he's not joking. This is real. I mean, he thinks he has hair. Oh my God.
And if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had to talk back? It's great. Yes.
Unlike ordinary computers, where each decision is based around a bit of information, and it's either 0 or 1, in the quantum world, the rule...
Because it's a lab, so they're in a lab. Oh, I guess they have to freeze the atoms. So yeah, it's got to be an actual lab.
change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
And you do quantum computing, you want to make this weirdness work for you.
No, it's not weird. We just don't understand it. Weird is not defined scientifically.
So now let's look at our quantum bit or qubit.
A qubit can not only be a 0 or 1, it can also both be a 0
0 and 1 at the same time. It's almost like a form of parallel computation, but in a parallel computer, one processor does this, one processor does that. So you have two processors doing this and that. Quantum computer is doing many processors doing this and that at the same time.
Yeah, that's nonsense. I don't believe it. That's a violation of the assumptions. So it's a self-contradiction. So it's nonsense by definition. La 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 la. But so what exactly did she do? She froze it? Slow light. Why does light slow down? Ask a spaceman. Paul Sutter, that's his name. Okay. General relativity. Fermilab. Why light slows and bends in glass? This guy's so funny. He's like a train wreck. He's impossible to avoid looking at.
Today I want to do a reaction video on a couple of Fermilab videos on why light slows or bends in glass or water or other transparent medium. And Don Lincoln did these videos, and he debunked a couple of wrong theories that
He called him Don Lemon? His name is Don Lincoln.
or water or other transparent medium. And Don Lincoln did these videos. And
No,
he debunked a
Lincoln.
couple
Okay, he called him Lincoln. That's fine.
wrong theories that you sometimes see on the internet, but he also got it wrong.
What do you mean wrong? Why? Why do you say that?
And he got it wrong because he took the bias of there is no quantum field, so there's no derivation of the quantum field. And in order to get...
He doesn't believe in the quantum field? What?
the right solution, you have to figure out why the speed of light is what it is in the quantum field, and then apply what you learn there to what happens.
In the quantum field? What do you mean it's what it is in the quantum field? I don't know. I don't know what you mean. I'm trying to imagine what you mean. So you're assuming that the quantum foam is what light travels through? That doesn't make much sense. In my theory, light travels through the ether. And there's also quantum fluctuations in the ether, but we also were waves through the ether. So the ether is the unified field. So everything we know about quantum fields is the ether. But light is not an artifact of the quantum foam. Light is the propagation of energy in the ether. The quantum foam is an artifact of the non-zero state of the ether. Everything that they say about the vacuum, I say about the ether. That's the difference between me and you. You say everything is about the quantum foam. The quantum foam is just an artifact of the ether. Now, I have experiments that can validate or disprove my theory. Do you? Have you ever presented an experiment that will disprove you? I don't think I've ever seen an experiment that you propose to disprove you. That's the first thing you should do.
Happens in glass or water. So we can start with what we know. The speed of light is a function of permittivity and permeability. E mu equals 1 over c squared. It's that simple. And so we need to think of the permittivity and permeability first, because that's another problem. Is he treats the speed of light like it's a constant, even when it's in water and glass, even though we know that it slows in water and glass. You know, that's one thing about scientific measurements. If you measure something slower, you should believe your measurement. You shouldn't say, oh no, it's not really slower. That's a nonsensical approach to physics.
Well, I didn't see his video, so maybe he said it's not really slower. I don't know. Maybe you're right. I don't know.
And so we can also know, as I discussed in other videos, the permittivity and permeability emerge from a polarizable quantum field. This is something Dickey mentioned in 1957, that when you have a polarizable medium, then those become fundamental constants, their emergent properties. And the way they come about is that if you have a bunch of dipoles, when a dipole rotates, it makes the other dipoles rotate. But they don't want to rotate, so it resists, so you get a torque.
But what are these particles that he always mentions this torque? I don't know. I don't understand what he's saying, so I'm sorry. I'm gonna go back. We have to take a break because I'm hungry. Does light slow down glass? Does light really slow down? Why is the speed of light a constant? Didn't we downvote? Yeah, we downvoted this guy. This guy's clickbait, yeah. Yeah, other people have noticed that this guy's clickbait. You are 6'9", 400 pounds, and booked the middle seat. This guy sits in coach? Isn't he like a multi-millionaire? Unifying gravity, magnet, electricity, dielectricity as one thing only? Who does this? Theoria Apophasis? How many people follow this guy? Wow, 311 million people. Oh my god. Newton's third law, best demonstration I've ever seen. Oh, there she is. So she's a professor, okay.
The speed of light is basically as fast as you ever get. What is it in American units? Something like 186,000
How do you know that?
miles a second. But in our clouds, we can slow them down to 38 miles an hour. That's what we did in our first experiments. And then we actually slow them down all the way to 1 mile an hour. And then you can basically crawl faster than light. What we do is we take a bunch of apps.
You can crawl faster than light. This is terrific. She's an experimentalist. I mean, she's okay.
Use what I call sodium amps, exactly what you have in table salt. And then we, of course, manipulate these amps in very special ways with laser beams. And then we can cool the amps down to a few billionth of a degree of absolute zero.
Okay, so. Okay, look, we can write it down as a method. Okay.
That's, of course, really freezing cold. It's actually the coldest place in the universe. And then once we create a cloud of such really cold amps, we illuminate that cloud with one laser beam. And then we send a light pulse in into the cloud from the other side. And we can now slow that light pulse down to the speed of a bicycle. And
so if light slows down so much, the question is for how long? How much total time? And will it give us a phase shift in the interferometer? Will we hold it there still for long enough to give us enough of a phase shift? We can write it down as a method, but we need to look at I just don't know the numbers. It's just a budget. Like, for what budget would you give me? I need to come up with a budget per degree per wavelength. Like, how many dollars for each degree for each degree, because the way I measure an effective, let's say we'll come up with a metric, and that is 1 degree per wavelength. Like, how close are we to 1 degree per wavelength? That's like the ultimate goal. For every degree, get a whole wavelength. If we can do that, I mean, that's unbelievable. I wouldn't aim for that. I would aim for 1 degree. Sorry, for 90 degrees single wavelength. That's my aim. That's good enough. If you can get 2 wavelengths per 90 degrees, 3, 4, 10, 20. At 90 degrees, 90 wavelengths, so it's every degree wavelength. That might be too much. We would need to be very gentle when we rotate the interferometer so that we see each wavelength. Otherwise, we're going to be skipping wavelengths. We're not going to see them. So we're going to need to be. We need to create a really sensitive apparatus. 1 second. I ran the scan. There's no threats. Okay. Okay. Let's see. Okay. So what is the budget? What's the budget? How many dollars do I need to spend to get a one wavelength per 90 degrees? That's the question.
Shocks along. And then if we feel like we can actually completely stop that light pulse inside our atom cloud, and then leave it there for a while, park it there, and then when we feel like it, we can send the light pulse back on its way, revive it, regenerate it, and out it comes.
How much does it cost?
What we're seeing is actually the atom cooler, really,
because then we would have an interferometer that does that to both beams, both directions. And that we should get an extra effect because of the ether. It's just going to give the ether. It's just going to give more of a chance to the ether to slow down. The light. It's just an extra effect, and we should be able to see it.
As I mentioned, we get these really cold atoms, and we need laser beams to do that.
All right. So what's going on here? What is this? She says that they're using laser beams to cool down. How do you use laser beams to cool down?
And then eventually all these laser beams that we see, they're really running around, crisscrossing the whole object state, and they all converge to the main vacuum chamber where the action is happening. And then we have up here behind, we have a very special atom source. That's where the sodium atoms are coming from. And they are not to start with. We have to keep them to create a gas of sodium atom. And at the time when we started to go after cold atoms, I did not have a clue that some years later I would start to look at slow light pulses. And that's really an example of if you get your hands on an exciting new system, that you start to cope with.
So she was able to get her hands on extra cold atoms, and then she looked for what can I do with it, and she said, "Oh, I can slow down light."
And see what comes out. And what you really hope is that something totally unexpected, totally exciting will come out. And I think that's what happened in this case.
Jesus Christ. Oh, there she is.
Thank you very much.
Bose-Einstein condensation and the taming of light. Lene Howe, PhD, Harvard University, Washington, D.C., May 11, 2011. So this is basically 10 years after she discovered it, the cutting edge, emerging trends in 5 fields of Bose. Okay.
So, well, you heard a little bit what I'm going to talk about. It's definitely changing gears here. As some of you might know, a very exciting area in physics in recent years has been studies and uses of ultra-cold atoms. We can these days bring cool atoms down to microkelvin and nanokelvin. That's a few millions to a few billions of a degree above absolute zero. That's pretty cold. And when matter gets, and we typically use lasers to do that job. That's sort of new techniques that have been developed. And when matter gets that cold, if you can sort of collect a bunch of particles or atoms, cool them down, they tend to form extremely strange states of matter. And a really good example of that is the Bose-Einstein condensate. It's a state of matter that Bose-Einstein predicted some 80 years ago, and it's only in recent years that it's actually possible to create this state of matter cleanly in the lab, first seen in the summer of '95 by Eric Cornell, Carl Reimann at Chile and Colorado. And I should say also that Bose-Einstein condensates, and I'll get back to more precisely what they are. Bose-Einstein condensate forms are also the reason explain why we have these strange phenomena such as superfluidity and superconductivity. This idea of superconductivity, that you can pass currents in certain materials at low temperatures, electrical currents we know will shift off. And that's of course an issue of great importance to this solve.
Wait, let me see what she wrote back.
Our energy problem, if we can start to pass electrical power long distances with minimal losses, that would be tremendous. So all of that, cosine condensates, that whole idea is really behind this phenomenon. Now, in my lab, what we have really been focusing on is to use this Bose-Einstein condensate to manipulate the stream.
So the Bose-Einstein condensate is the prediction of superconductivity. Okay, I don't know how that works.
I will tell you a bit about how we go about slowing light to the speed of a bicycle, just as you heard in the introduction. And I'll also tell you some of our more recent stuff where we stop and extinguish a light pulse in one part of space, and then we can regenerate the light pulse in a completely different location and in a diagonal way. So to do this kind of experiments, of course, we need some cold atoms, and with the kind of temperatures we are talking about.
Okay, I mean, I don't want to get too bogged down. I just wanted to make sure she can do it. I wanted to get an idea of the budget. The question is, can we implement an interferometer based on her stuff? Anyway, so it is possible, I would say. That's my intuition. We would need to look into it. So if anybody wants to pursue it and you want to write a paper, your PhD on this, you're welcome. You can credit me below. Like, you can give me the credit that I came up with this notion. So she said, what can I do with super cooled atoms? Oh, I can slow down light. And I'm coming and I'm using her technique to build an interferometer to prove the ether. So if you do that and credit me, I would thank you. Otherwise, you're plagiarizing. Okay, let's stop here. And hopefully in the next video, I'll have a chance to actually explain. We'll do a diagram. Maybe we'll do a diagram of this method as well, of each method, but at least of the simplest method that I think is available, that is using fiber optics. All right, let's stop here. I'll see you later. Bye.